Today we are continuing the geometric modeling course, and the topic of our lecture today is algorithms for contour maps and isosurfaces. The current lecture covers the following topics: its basic definitions of contour map and algorithms for contouring and polygonization. First of all, let us to give a definition of a contour line and a contour map. Let's give a function f of two variables x and y, plus two linear scalar arrays xi and yi, and also constant levels ck. A contour line of a function of two variables is a curve along which the function has a constant value. Other words, contour is an implicit curve or several curves. So we can say that curve joins point of equal value. A contour line has other terms. It's contour or isoline or isocontour. Contour map is a set of contour lines. Examples of contour map can be topographic map or two-dimensional contour graph of a three-dimensional surface. Contour is defined with a surface z, which is function of two variables, a plane which is defined by constant value of z, an intersection between the surface and the plane, and projection of the curve onto x and y plane. Let's imagine that we calculated the values of function z in every point of regular grid, for example 4 by 4. Also the contour level was chosen. It equals 0. The next question is how to construct a contour using calculated values on a regular grid. The first step, we need to find edges in every cell of grid where function change its signs. After that we need to find points in every edge where function equals 0 using linear interpolation or numerical methods. And the third step is to connect to these points and obtain the line segment or piece of contour. The general steps of the contour generation is represented on this slide. The first step is selection of the cell with intersection point, where plane intersects the function z. If no cells to process, then the end of the algorithm. The next step is processing a cell and constructing segments of the contour. Next, repetition of the first step. The first simple method of contour construction is exhaustive enumeration, when we process cell by cell on the grid. Other methods for reducing computation we consider further. Now let's consider exhaustive enumeration example. We construct the contour sequentially by processing every cell which has different signs in its corners. The cell processing algorithms is following. Find all edge surface intersection points. They will be vertices of contour lines. Connect vertices into segments. Add segments to the contour or render segments. For searching the intersection point on the edge of cell where function f is equal to 0, the linear interpolation can be employed. On this slide the edge is marked by blue color. The parametric equation for the line segment using 2 points x1 and x2 can be constructed as shown on this slide. The intersection point xp can be found by solving this linear equation. The linear interpolation allows to get approximated points of contour, but real values where function equals 0 can be laid in other places on the every edge. For searching intersection points with certain accuracy, we can use analytical solution for polynomial f or numerical methods for solving nonlinear equations such as bisection or Newton search. There are two typical cases in the cell. The first one when we have 2 intersection points, and the second one when we have 4 intersection points. On this slide, all cases of intersection points inside a cell are represented. The black points, closed points, in the corners of the cell mean negative values of a function. The open points mean positive values of a function. This lookup table is used in an algorithm called Martian squares, a simplified two-dimensional version of the Martian cubes algorithm. There is a topological ambiguity in case of 4 intersection points, because we have two ways of points connection. How we can solve this ambiguity? Which way is correct? We will try to answer that question. Two possible contours with one ambiguous cell are represented on this slide. The function in such type of cell can have disjoint contours as shown in example A, or can have one complex contour as shown in example B. The topological ambiguity example is shown on this slide. The topological ambiguity example in real life is shown on this picture. This is worst case of a contour map for the contouring algorithm. The resolving the ambiguity of cell with 4 intersection points can be done with using hyperbolic arcs. There are 4 steps of this method. The first one is the bilinear interpolation inside the cell. After that, the construction of contour as a hyperbola. Then calculation of the hyperbola center, and using the center of hyperbola to resolve the topological ambiguity. In this method, we approximate the defining function f with a bilinear function inside the cell. The proposed approximation works better for smooth defining functions. The function f is a description of a hyperbola. The polynomial can help to find the center of the hyperbola. So we have 4 points of hyperbola for resolving ambiguities. For proper selection of hyperbolic arcs, we need to compare u0 and u1. Let's take a step forward and increase the dimensionality. Now let's talk about the isosurface extraction algorithms. Isosurface has other terms: implicit surface, 3D contour, or equipotential surface. An isosurface is a three-dimensional analog of an isoline. It's a surface that represents points of a constant value with a volume of space. In other words, it's a level set of a continuous function whose domain is 3D space. There are two ways of isosurface rendering. The first one is direct rendering when we obtain two-dimensional image of isosurface. For example, the ray tracing algorithms can be used here. The second method, when we construct the point cloud or curves of polygon of the isosurface, and after that do rendering of this shape. Let's consider the isosurface polygonization. Polygonization is the generation of a polygonal approximation of an isosurface. You can see the example of polygonization of this slide, where the continuous function is represented by a set of triangles. The simple way of isosurface polygonization can be performed using exhaustive enumeration. Discrete data, voxel data from CT or MRI, is usually a set of points with scalar values in the nodes of a regular and uniform grid. Exhaustive enumeration examines every cell, determining which cells intersect the surface. This method is fast because data values are known. Intersections of surface with edges are usually computed by linear interpolation. But for n-cube cells and n greater than 1000, memory management becomes a problem. Example of such exhaustive enumeration algorithm is Martian cubes algorithm, which processes a rectangular grid one plane at a time. Each cubic cell is polygonized according to a 256 entry table of ready polygon configurations. Cell polygonization generates a set of polygons for the surface patch inside a single transversal cell. Steps of the cell polygonization are the following. The first one is to detect a cell edge which intersects the surface, different function signs in the endpoints. Such edge is assumed to contain a single intersection. The next step is to compute an intersection point, surface vertex. And the final step is to connect surface vertices to form polygons. For surface vertex computation, the linear interpolation and binary section, binary subdivision, can be used. Surface vertices connection algorithm starts with transversal edge. Look for the next transversal edge in the face and stop when the polygon is complete. Let's consider the lookup table for the surface vertices connection. The configuration of the set of polygons for a cubic cell depends on the number of cell corners with positive function values. For 8 corners there are 256 possible configurations, but only 15 basic configurations have to be stored. Others are equivalent to them due to symmetry and rotations. As for two-dimensional case, the topological ambiguities exist for three-dimensional case, but such variants are more than in two-dimensional case. Ambiguity occurs for certain configurations at the cell level. Examples of such ambiguities are shown on this slide. Let's consider the polygonization algorithm with hyperbolic arcs. The input data for this algorithm can be continuous and discrete data. For spatial partitioning, the exhaustive enumeration with the given number of cells for each axis is used. The linear interpolation of binary search can be used for surface vertex computation. For the surface vertices connection, the algorithm of a connectivity graph construction and tracing can be employed. For the ambiguity resolving, the trilinear interpolation is used in the cell, and local bilinear interpolation is used on the cell face. Connectivity graph construction contains 6 steps. The first step is processing of 6 cell faces independently. The second step is resolving topological ambiguities on each cell. The third step is constructing a graph with 12 nodes representing edge of the cell. Nodes in the graph are connected if there is a hyperbolic arc connecting them on some face. Finally, find all cycles in the connectivity graph. They correspond to the polygons. Let's consider other methods for contouring. These methods have reduced computations compared to the exhaustive enumeration, but have their own drawbacks. The first algorithm is predictor-corrector continuation. The second algorithm is subdivision of space, and the third is shrink-wrap algorithm. The predictor-corrector continuation works as following. We have to select an initial contour point, calculate the tangent line, make step along the tangent direction, its predictor, correct the selected point by search in the normal direction, its corrector, connect the previous and the new points by a segment. There are such problems with this algorithm. It's difficult to get contour with high curvature areas. And if there are disjoint areas or multiple components, we cannot extract all contours using a single point. The next method is subdivision of space. It allows to extract a contour without exhaustive enumeration by using spatial data structures such as quad tree or oct-tree. This method contains the following steps. First of all, we need to define a bounded box for the contour. It's called original cell. Next step is subdivision the cell in 4 subcells. After that, to check all subcells for their contour intersection. And repeat step 2 for all non-empty subcells. Finally, we will obtain the collection of cells enclosing the contour. The third method of contour extraction without exhaustive enumeration is shrink-wrap algorithm. It contains the following steps. The first one is definition an external polygon. The second one is moving its vertices to the contour. The third one is subdivision its edges, and repetition steps 2 and 3 until the given precision is reached. The problems of this algorithm are the same as in the algorithm with predictor character. As an example of the implementation of the above-mentioned algorithms, we can give an open project called Hyperfun Polygonizer. It takes function f of three variables x, y, and z in special Hyperfun language. It extracts a polygonized isosurface as a triangular mesh using polygonization algorithm with hyperbolic arcs. This triangular mesh is rendered with OpenGL and can be exported in VRML and STL formats. On this slide you can see a piece of code in Hyperfun language describing an abstract shape, its sphere with additional noise, and below there is a rendered image of the shape. Here is a list of references where you can find additional information about algorithms for extraction of isocontours and isosurfaces.